Continuing our discussion of replication control, in this lecture we will see an important technique for committing transactions in replicated systems. This is known as two-phase commit. In general, committing transactions is an important problem in replicated systems, and in general in systems where you have objects across distributed servers. So here's an example of a transaction that touches objects at multiple servers. Here in this case we ignore replication for now, but let's just say each object has only one replica. So there is 26 objects here, there is 13 servers, each storing two of the objects. So server 1 stores objects A and B, server 2 stores objects C and D, and so on and so forth. Server 13 stores objects Y and Z. The transaction T here writes to all of these objects. When it reaches its commit point, we need to make sure that all of these servers commit. Okay, so when T tries to commit, we need to make sure that all the servers commit their updates. In this case, T will actually commit, the transaction T will commit, or that none of these servers commit their updates to their objects. In this case, T will abort. Okay, so this is an example of an all or nothing property here, which we want to guarantee for the transaction, but we also want to guarantee on the server side in a group of servers with distributed objects. This problem obviously should be familiar to you. This is in fact nothing but the consensus problem. In fact, in the concept of transactions, it's known as the atomic commit problem here. So one way to do an atomic commit is known as one-phase commit. This is a first-cut, naive approach where you have a coordinator server, say a special server elected using leader election protocol, your favorite leader election protocol. The coordinator server is a special server that initiates the atomic commit and simply tells the 13 servers involved here, hey, why don't you commit your object updates from transaction T? If something goes wrong from the transaction side, if the transaction T wants to abort, then it tells the coordinator server to abort, and the coordinator server then relays to the servers that they should abort their updates from transaction T to their objects. So what's the problem with this? Well, the first issue is that the server storing the objects, the servers 1 through 13, have no say in whether the transaction commits or aborts. These servers are after all machines, so they have memory, and the memory might be corrupted. For instance, the object that they're storing or the updates from that particular transaction may be corrupted, and in this case you'll end up with an inconsistent system, because as far as the transaction T and the coordinator are concerned, they have wanted to commit, but the server just cannot commit. It just cannot commit because it does not have all the necessary information there. Also, the server might crash before receiving the message that asks it to commit, and in this case the updates it had from transaction T might have been stored in memory and lost. And in this case, you again have a system where you have data being lost. So to our rescue comes the two-phase commit protocol, which to this day is one of the most widely used protocols for committing transactions. Here again you have a coordinator server, again elected using a leader election protocol, and you have the remaining servers. As the name suggests, instead of using just one phase where the coordinator tells the server group, you have two phases here. So the coordinator first sends a prepare message to the servers. The prepare message asks the servers to prepare to commit. When a server receives the prepare message, it saves the updates from that particular transaction to disk so that it is durable now. And after this, if the server fails, it can then recover starting from this log on disk. Then if everything is okay on the server side, it responds with a yes vote. If something went wrong, for instance, the memory got corrupted or it has lost its updates, it responds with a no vote. The coordinator server waits for these votes. If it receives any no vote, at least one no vote from any of the servers, it will then send out an abort message to all the servers. Okay, so this ensures that unless all the servers have voted yes, you will in fact end up aborting the entire transaction. Also, the coordinator server might not receive all the votes within a timeout. If it does not receive all the votes within a timeout, it also again sends an abort message to everyone. This is accounting for the case where a server might have failed. Server 13 might have failed and might never be able to send a vote back, and in this case the coordinator must abort because it doesn't know what happened, what went wrong with server 13 and whether server 13 will ever come back up. Okay, so once again, in summary, if the coordinator server receives at least one no vote, or it does not receive all the, in this case 13 votes within the timeout, it will send an abort message. However, if it receives all the 13 votes within the timeout, it then sends out a commit message knowing that everything has gone right on the server side, and they have saved their updates to the log on disk. Once they have voted yes or no, they can't immediately go ahead and commit, right? So if they voted yes, they can't really commit before receiving the next message. Okay, so they need to wait until the second phase commit message is received. When the commit message is received, they can then commit the updates from disk to the store, to the actual database, and they can respond back with an acknowledgement back to the coordinator. When the coordinator receives all the acknowledgements, okays, it can then say that the two-phase commit is done. How do you handle failures and how do you make sure that correctness is guaranteed? So first, if a server, one of the 13 servers in our case, voted a yes, it cannot unilaterally go ahead and commit the updates from the disk into the store or into the database. It needs to wait for the commit message. Why is this? Well, one of the other servers in the group might have voted a no or might have failed. In this case, the server might have to abort in the future. However, if a server votes no, meaning something has gone wrong on its side, if it votes no in the very first phase, then it can abort right away. Why is this? Well, this is because the coordinator would have received at least one no vote, this server's, and so it would have decided an abort in the future. Okay, so no matter when that abort is decided, it will never be a commit because this server has voted a no. Okay, so if a server votes no, it can go ahead and abort right away, but if a server votes yes, it needs to wait until the commit message is received. How do you deal with crashes? So to deal with server crashes, each server saves the tentative updates into permanent storage, meaning disk, right before replying yes or no in the first phase. It can't save it after replying yes or no because it might fail right after replying yes or no, but before saving it on disk. It needs to save it on disk before replying yes or no. If it fails before this, before it saves it on disk, anyway, the coordinator will time out waiting for this server's response and will abort the transaction. If it times out, if it crashes after saving it on disk but before replying yes or no, again, that's going to be an abort decision. If it crashes after saving it on disk and sending a yes vote, then it might be a commit decision, but at least it has all the necessary information saved on disk so that it can recover or retrieve it after its recovery, after it is rebooted. The coordinator might also crash, and so to recover from these crashes, the coordinator also logs all of its decisions and the received and sent messages, including counts of how many OKs it received on disk, so that if it fails, it can then recover and start where it left off. However, things might go wrong and the coordinator might never come back up, so a new election might be required to elect a new coordinator. In this case, the coordinator might need to either start where the old two-phase commit left off by querying the servers or just restart the two-phase commit altogether again. What about message losses? The messages that are sent out during the two-phase commit might also get lost. The prepare message, which is the first stage message going out from the coordinator to the servers asking them to prepare to commit, might get lost. Now, if the prepare message gets lost, then the server, one of the 13 servers, might decide to abort unilaterally after a timeout, waiting for the first phase message. In this case, because it will never vote a yes to the coordinator will always decide an abort for this particular transaction. Alternatively, to deal with prepare message loss, you can have the coordinator send out a second prepare message. Now, the yes-no vote in the first phase again might get lost as well. If this gets lost, then the coordinator will end up aborting the transaction. This is tough luck, even though everything might have gone right, even though everyone might have voted yes, just because the message, one of these yes votes was dropped by the network, you decide to abort the transaction. Yes, this is pessimistic, but at least it maintains correctness. It errs on the side of safety. And in this case, the coordinator, unless it receives all the votes, will decide to abort the transaction. Finally, the commit or abort message, the second phase message, might get lost in the network itself. And in this case, you're okay because the coordinator has already made a decision and has logged the decision on disk. So the server can poll the coordinator if it has not received a decision in the second phase for what its decision is. Okay, so it can poll it repeatedly until the coordinator comes back up and sends it either a commit or an abort message. So a two-phase commit is used at the commit point in distributed servers. Another alternative to two-phase commit, of course, is a consensus solution such as Paxos. So Paxos is also being widely used nowadays, increasingly used nowadays, to decide whether to commit a transaction or not. Okay, but if you use Paxos, you need to make sure that if any server votes a no, then everyone will abort. That's the only catch in using Paxos. Paxos can also be used for ordering updates that are being received by a replica group. So when a replica group receives multiple updates from multiple clients, you need to make sure that all the replicas receive the updates in the same order. This is again because of replicated state machines. You want to make sure that all the replicas have the same series of states that they transition through and the same series of outputs. So in order to do this, essentially the way you use Paxos is that a server, any one of the servers in the replica group, proposes a message for the next sequence number. So one of the updates it has, it proposes it for the next sequence number, and then the group either reaches consensus on this or not. If it doesn't, then another message is considered for the next sequence number, and you continue so on and so forth. Okay, so this is the way in which Paxos is used to totally order updates within the group itself, so that all the servers apply these updates in the same order as each other. So that wraps up our discussion of concurrency control and replication control. For replication control, we've discussed the case where you have multiple servers, distributed servers in the cloud, which are either replicating objects for fault tolerance or load balancing objects across multiple servers with or without fault tolerance. Replication can be implemented using a couple of flavors, active replication and passive replication, and these can be implemented using concepts that you have learned earlier in the course, specifically using flavors of multicast and virtual synchrony. And finally, we have seen how to commit transactions when you have distributed servers in the cloud. The two-phase commit protocol is one of the most widely used protocols today.